Watch this rate law expression. Here, x and y are the factors which are called order with respect to the reactants. Therefore, x is order of reactant A and y is order of reactant B. Therefore, order is actually a factor which is raised to the power of the concentration of a particular reactant such that it determines how the concentration influences the reaction rate. When we add x and y, we get the overall order of the reaction. The order of reaction may be 0, 1, 2, 3, and even fractional values. Negative orders are also there, but negative orders seldom used to calculate overall reaction order and will not be discussed here. Now, it is a little difficult to perceive zero order and fractional order reaction. Let me give an example of each. Look at this reaction. This is a catalyzed reaction. There is an example of heterogeneous catalysis where the reactants are in the gas phase and platinum metal catalyst is the solid phase. Reaction occur at catalyst surface only. Suppose theta be the fraction of catalyst surface covered with gas molecules. This theta will control the reaction rate. This is the fraction of a surface uncovered and control the rate of adsorption of gas molecules on catalyst surface. The rate of adsorption also depend on the gas pressure. The rate of desorption will depend on theta. At equilibrium, both the rates are equal. After some calculation, we get the rate of equation like this. At low concentration of ammonia, this factor is neglected and the reaction follows first order kinetics. At a high concentration of ammonia, one is neglected and the reaction follows zero order kinetics. This is fair enough, as we know that a reaction only happens at the catalyst surface, and when concentration of ammonia is high, the catalyst surface is saturated with ammonia molecules, which is constant since catalyst surface is constant. Consider this reaction. This one is a complex reaction and the mechanism involves three steps. The mechanism shows formation of chlorine free radical which react with chloroform to form carbon trichloride free radical as the reaction intermediate. The second step is slow and is the rate determining step. So this is the rate expression. The chlorine free radical is also a reaction intermediate which cannot be seen in the overall reaction. So this has to be eliminated from the rate expression. We get its value from the first step, which is reversible. Replacing this value in the rate expression, we get this rate expression which contains the concentration of reactants of the overall reaction. Order with respect to chloroform is 1 and order with respect to chlorine is half. Overall order is 3 by 2. Now just look at the rate law expression, which is also called differential rate equation due to these differentials. This rate is the instantaneous rate, which means that the change in reactant concentration within an infinitesimally small time gap. In my previous video on the same subject, I had mentioned that the initial rate of a reaction has to be experimentally determined in order to establish the rate expression. However, practically it is impossible to determine reactant concentration after a very small time interval. What we actually measure is the average initial rate and not the instantaneous initial rate. So there always exists some error in establishing rate law expressions and finding out the correct reaction order therefrom. So differential rate equation cannot be practically established for determining instantaneous rates and order of reaction. To overcome these practical difficulties, we integrate the differential equation. What we get is called the integrated rate equation. We do this for different reaction orders. For zero order reaction, the rate is independent of concentration. Concentration versus time curve is straight line and the slope is negative of rate constant. For first order reaction, the logarithm of concentration when plotted against time give a straight line, the slope being equal to negative of rate constant. Here rate constant may be calculated accurately from this equation even though the time interval is not small enough. Reaction of the nth order is integrated like this. The equation is applicable for all reactions except order 1. Here when this is plotted against time, It will give a straight line. The slope will be this. Integrated rate equation for second order reaction having two reactants A and B is integrated like this. If you know calculus, you will be able to understand this stuff. Half-life of reaction is the time taken for a chemical reaction when the concentration of the reactant becomes exactly half of the initial concentration. It is denoted by T half. Half-life of a reaction depends on the initial concentration of the reactant and the order of reaction like this. Exception is first order reaction where a reaction proceeds in the same manner whatever is the initial concentration. If half-life of a particular reaction can be measured with two different initial concentrations, then the order of that reaction may be found.